State and prove Laurent expansion. So the statement of this theorem is, suppose a function which is fz is analytic in an annual region R1 less than modulus of z minus z naught less than R2, then fz can be written in the series expansion that is written in the equation number 1, where an is equal to 1 by 2 pi iota integration around C2 and Bn is equal to 1 by 2 pi iota integration around C1. What is C1? C1 is a circle of radius R1, and what is C2? C2 is a circle of radius R2. Now this is the statement. Now first we understand the statement of our question. Now in the given part, this function f of z that is given, and this function is analytic in this yellow region. So this is a white circle whose radius is R1, this is a red circle whose radius is R2, and that circle is named as C2 and white is named as C1. So this function f of z, which is analytic in the annual region which lies between R1 and R2, so that is a yellow part. So this is a analytic in this region. So in the previous result, we discussed the Taylor expansion, the series expansion of an analytic function. Now this is the theorem where it has singular point. Now this z naught is a singular point of function fz. Means fz is not analytic at z naught, but it is analytic in the yellow part. So how we can expand this analytic function in the series expansions? Now the function fz is analytic in the yellow part, then the by Cauchy integral formula. So by Cauchy integral formula, so this can be written as by Cauchy integral formula, f of z can be written as 1 by 2 pi iota integration of fs into ds, s is variable, and here s minus z. This is around C2 integration. So bigger circle minus 1 by 2 pi iota integration around C1 f of s over s minus z into ds. So this is a smaller circle of radius r1. So this is a C2 and this is a C1. Now what is my aim? My aim is to convert it in the binomial expansion. Before going to that expansion, first we add z naught in these terms. So we will add the singular point z naught in this term in this way. C2, which is f of s into ds over s minus z naught minus z minus z naught. Z naught, this z naught is cancelled to each other. Similarly, 1 by 2 pi iota, this is around C1, f of s into ds over s minus z naught, and this is minus z minus z naught, this values. Now this term and this term, find the relation between these terms. These terms mean find the length of these equations. Now, when the circle is C2, so just when the circle is C2, so this point is S2, S, and point Z is at this place. So what we get? We get this Z minus Z naught is greater than S minus Z. That Z minus Z naught is greater than S minus Z. So what we get? We get S minus Z naught over Z minus Z naught is less than 1 on circle C2. I repeat this concept again. Now here it is S point and here it is a Z which is on C2. So S minus Z naught is less, have lesser value than Z minus Z naught. So this over this is less than 1 on C2. Similarly, when in case of C1, this is a C1. So this point is Z. Suppose this point is Z. Now in this case, this point is Z. If this point is Z, then Z minus Z naught over S minus Z naught is less than 1. So in the another case, Z minus Z naught over S minus Z naught, this value is less than 1 on C1. So remember that. So it means in order to apply binomial expansion, in this case, in this region, we will form the series in this form S minus Z naught over Z minus Z naught, and in this region we will form the series in this form Z minus Z naught over S minus Z naught. So then what we will do? So we will do by taking these part in my mind. So when we are discussing the about C2 region, so then in that case I will take 1 by 2 pi iota these values. Now here what is my requirement? Here it is a C2 region. So in the C2 region my requirement is Z minus, this is Z minus Z naught. So this value it should be in this case Z minus Z naught less than over S minus Z naught less than 1. So my requirement is in this case Fs into ds over this values S minus Z naught and this value which is 1 minus Z minus Z naught over S minus Z naught, this values. So I will repeat the another concept. So I will take this values and this ds is outside because this series involve the ds. So I will take ds is outside these values. So just will repeat why I am taking s minus z naught is outside. Now just check that again. In this case, we have two circle. One is this circle which is a C1 circle and second is C2 circle. So this is a bigger circle. So which is a C2 circle, right? So in this case, Z minus Z naught is less than S minus Z naught, this values. Now this term S minus, this point is Z naught, this values. So this point is if on C2, so this S is on C2. So this S is on C2 and this point is Z is in this region, in this region. So S is on C2, Z is on in this region. So it means S minus Z naught is larger than this. So in this case, Z minus Z naught over s minus z naught, this value less than 1 on C2, this value on C2. Similarly, in the second part in C1 region, it will be reversed. So in that case, S minus Z naught over Z minus Z naught, this is less than 1 on C1. How? Because in this case C1, S point is on this place, S point on this place. If S point is on this place, so S minus Z naught over Z minus Z naught is less than 1 on C1, right? So here I take a wrong S. So in this case, S minus this first part, this is on C1. So this is on C2. This is on C2. So just so this value, correct this, it is on C1 and this is on C2. So I once again repeat this concept. So when we are taking on C2, so what is integration? Integration is in a variable S. So S will be on C2. Z is in the region. Similarly, when we are taking the C1, so S is on C1 because integration, the variable of integration is S, so S is on C1. So in this way, we can write this values. Now, so by taking this in our mind, so this can be written as 1 by 2 pi iota. Now from this I will take minus z naught. So this will become a plus. So this is C1 f of s into ds. So we will take ds outside. So z minus z naught, and this value is 1 minus s minus z naught over z minus z naught raised to power minus 1, right, into ds. Now this term is less than 1 in this case and this term is less than 1 in this case. So we will apply the binomial expansion. So by applying the binomial expansion, this series will become as f of z. So this is a f of z which is equal to 1 by 2 pi iota, and this is integration around C2. So here it is f of s over s minus z naught, this values. Again this is bracket. In this bracket we will have a series of binomial expansion, so which is summation of n running from 0 to infinity, and this value is equal to z minus z naught over s minus z naught, and this raised to power n and into ds. So this is my first part. Second part, this is 1 by 2 pi iota, and this is integration around C1. So this will become a f of s, and the term is here z minus z naught, this values, and this term will become, this is in bracket, this bracket. In this bracket we have the series which is from s minus z naught over z minus z naught raised to power n, where n is running from 0 to infinity, and this term is into ds. Now we are very near to our result. So we get this values. Now again simplify this equation. So here summation can be taken outside. So what we get? We get first term f of z. So in the first term, summation is 1 by 2 pi iota. So this is constant term 2 pi iota. Second is summation, which is n is running from 0 to infinity, this term. And after that, integration C2, this is a C2 integration, f of s into z minus z naught, and this is raised to power n over s minus z naught raised to power n plus 1 into ds, this values. So this is independent from this, so I can take it outside. So here also I may be written in this form. So this can be written in this way. If I take this is as outside because it is independent from z. So this is can be written as z minus z naught raised to power n plus 1. Z minus z naught raised to power n. So this kind, so this 1 by 2 pi iota I will introduce inside. So 1 by 2 pi iota. So I will remove from this side. So this side will be, I will taken it inside because it is the this value is equal to this values. Now this term is taken in the bracket. So this term is taken in the bracket, this values, because this is summation 1 by 2 pi iota and this values into z minus z naught. Now here this, when we multiply by this, so this will become a, this will become a z minus z naught raised to power n plus 1. Now this equation, now the second equation can be written in this way, plus summation of this value n, which is running from, if I remove this values, n is running from 0 to infinity, this values, and this value can be written as 1 by 2 pi iota, 1 by 2 pi iota integration around C1. This is f of s into ds over s minus z naught raised to power minus n, and this is bracket 1 over z minus z naught raised to power n. So this is z minus z naught raised to power n plus 1, this values. So in this way I write this term. So this is, so here it will be 1 n, because this value is equal to this values. So simplify this value. So this value will convert into this raised to power n. Now if I change this number from n equal to 0 to infinity, if I change this values, so this is z minus z naught raised to power 1. If I take this summation from 1, if I take this summation from 1, so this is from 1, then this will be changed as n plus 1 this is as 1, and this is again n plus 1, this term. So minus n plus 1, and the next term will be the n plus 1. So this term, and then it will be the n. So this term will be the n. So just do calculation in this. So this will be when summation is n running from 0 to z minus z naught raised to power n, and s minus z naught, it is raised to power minus n. So this is if from 0, so s minus z naught is this is from raised to power, if it is from 0, so this is from z minus z naught raised to power n plus 1, this is n plus 1, and s minus z naught, this term here we check that this is a s minus z naught raised to power minus n. So this is first I take in this form 0. So this, so to avoid the confusion, so I take in this way. So this value is n plus 1, this values. Now this term can be written as bn. This term is treated as bn, and this term is n plus 1, this values. So when we start from the 1, if this summation is start from the 1, then it means at this place it is a 0. So this will be minus 1. This will be change n into n plus 1. So this will be minus 1, and the other term, this will be n. This term will be n. So this term will be minus n, this values. Now this can be written as in this way. So this can be written as f of z, this is f of z, first term, summation of a n z minus z naught raised to power n, where n is running from 0 to infinity. So what is a n? So I take this term is a n. So this term is a n. If this term is a n, summation of n running from 0 to infinity, a n into z minus z naught. So what is a n? So a n I write a n, which is 1 by 2 pi iota, which is C2 f of s into ds over s minus z naught raised to power n plus 1, this value. So this is the C2. Now what about the C1? So in this case, if we start this mission from 1, so this n will be converted as n plus 1, here n plus minus n plus 1, here n plus 1 when we start this mission from n equal to 1, right? So it means this can be treated as, this is a bn. So this is a summation of bn over z minus z naught raised to power n. So this will be raised to power n when we start from n, because it is n plus 1. Now this is n is running from 1 to infinity. So what is the bn? So bn, which is equal to 1 by 2 pi iota integration of C1 f of s into ds over s minus z naught raised to power, the difference between that is minus n plus 1. Here it is plus 1, here it is minus 1, and here summation is running from 0, 1, 2, so on up to infinity. Here summation is running from 1, 2 and so on up to infinity. So this is the Taylor expansion. So first I go to the statement of the Taylor expansion to check that. So in this way, this is the value of an and this is the value of bn. So just I used simple. So this is, so correct here, an is equal to n plus 1, n is 0, 1, 2. Here n is a minus 1. So minus n when n is 1 to so on up to n. So just make correction in the this statement. So the I repeat, so function can be represented as summation n equal to 0 to infinity, summation n equal to 1 to infinity, where an is of this kind and bn is of this kind. So in this way we can prove our result. Now after that, if we used the property of transformation of path by using the property, so this is a remark of this theorem. So what is the remark of this theorem? So by using the property of transformation 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 of the path, property of transformation of path C1, of path C1 and C2, C1 and C2 replaced by a single path replaced by C. How we will do that? So this is a one path C2 and this is a second path C1. If I have the path lies between that, so which is a C, so this integration is equal to integration of C, this integration is equal to integration of C. So in that case, f of z, which is a series, summation of a n z minus z naught raised to power n is running from 0 to infinity, plus summation of bn over z minus z naught raised to power n is running from 1 to infinity. The difference is here it is started from 0, here it is started from 1. And in the combined form, this can be written as, in the combined form, this can be written as summation of Cn, which is z minus z naught raised to power n. Here n is running from minus infinity to infinity. So check that this series can be written in this way. Now, where Cn, which is equal to 1 by 2 pi iota, this is, now here integration is C, f of s into ds over s minus z naught raised to power n plus 1, and this is basically an, this term is an, this can be written as equal to b minus n. So this is an where an is equal to b minus n. So just replace minus n into minus n. So this series can be written in this way. So this is the proof of Taylor theorem, which is very important. Now how we will apply the Taylor theorem for the expansion of any function which has a singular point. Now for example, derive the first statement is derive Laurent series. Derive Laurent series of the function number 1 a. This function value is f of z, which is equal to z cube cos hyperbolic 1 by z, and second is b, which is f of z into 1 over z square 1 minus z. So in order to solve these expansion, so remember the sum standard expansion that we find in the form of Taylor expansion. For example, e raised to power z cos z sin z cos hyperbolic z sin hyperbolic z 1 over 1 minus z 1 over 1 plus z. So remember all these series. So we will directly apply to this series to solve our question. Now this. Here z equal to 0 is the singular point. Here we have two singular points, 0 and 1. But here z equal to 0. So I need a expansion around 0, right? In this case, so I need a expansion around 0. So we know that cos hyperbolic z. We know that the formula of cos hyperbolic z. So this is the first term is 1 plus z, even term z square by 2 factorial, z 4 by 4 factorial, z 6 by 6 factorial, and so on up to infinity. In series form, this can be written as z raised to power 2n over 2n factorial, and this is n is running from 0 to infinity. So that we know the formula in this form, where 0 less than modulus of z less than infinity in the entire region. Now in our question A part, my requirement is cos hyperbolic 1 by z. So simply replace z by 1 by z. So I get, if I write in the series form, so series form n equal to 0 to infinity 1 by 2n factorial into 1 by z raised to power 2n, this values, this. And second is we multiply by z cube, this is z cube, and then here multiply by z cube, so this is z cube. So what we get? We get our new function summation n running from 0 to infinity 1 by 2n factorial 1 by z raised to power 2n minus 3. So that is my result. So this is a series expansion of fz around the z equal to 0. So this can be written as, it implies the function f of z. This can be written as about the expansion of z. So this is a summation of n running from 0 to infinity into 1 by 2n factorial into z raised to power 3 minus 2n. So this is my first question of Taylor series. Now second is, for a given region, the second part is to find the series expansion f of z. So f of z, which is equal to 1 over z square into 1 minus z, where 0 lies between, modulus of z lies between 0 and 1. So here it is very important. So our requirement is series in term of z. So this equation is already in term of z. So I need this equation in term of z. And this will be expanded as binomial if modulus of z less than 1. So that is a given part. So solution of this type f of z, so this is equal to 1 by z square into 1 minus z raised to power minus 1. Now since modulus of z less than 1, otherwise it is not possible, then this can be written as 1 by z square 1 plus z plus z square plus z cube plus z raised to power so on up to infinity into this values. In this way, in this region, we find this values. So the series is of this kind. So this is a kind of series. This is z raised to power n minus 2, where n is running from 0 to infinity. So that is my first part. So this is in this region. This is in this region. Now if the region is changed, now in the second case, if in this series the region is changed, so region will be modulus of region for region modulus of z less than 1. Remember that. So in this case, it implies 1 by z modulus is less than 1. So we will apply binomial on this variable. So what is the function fz, which is equal to 1 by z square into 1 minus z? Now my requirement is 1 by z. So take minus z outside. So this will become minus 1 by z cube over 1 minus 1 by z raised to power minus 1. So apply binomial equation, minus 1 by z cube. So this is 1 plus 1 by z plus 1 by z square plus 1 by z cube and so on. So this is a series in the case of this region. So this may be written as, this is n plus 3. So this may be written as minus summation of n running from 0 to infinity. So this is 1 by z raised to power n plus 3. So this is written in this way. So by using the previous expansion, standard expansion, we can easily find the series, in case of Taylor expansions.